Hello! Today we're diving into buckling in finite element analysis, also known as FEA. When loaded in tension, a bar will fail when the normal stress is greater than the yield or tensile strength of the material. When loaded in compression, the bar will fail when the compressive strength of the bar is exceeded, or the bar can fail by buckling. But what's buckling? Buckling refers to the sudden and often catastrophic failure of a structural component when subjected to axial compression. This phenomenon is encountered in a variety of mechanical systems, from thin-walled structures to columns and pressure vessels. Buckling can be characterized by sudden deformation and large displacements. The deformation that buckling can cause does not always result in yielding or fracture, but buckling is still considered an important failure mode to consider, because once a member buckles, it is unable to support the load it was designed to support. Columns are often used as a simple example of where buckling can occur, but buckling is present in many other applications. On the left, we see two columns that have buckled, and on the right, we see an example of a truss member buckling. Train tracks can buckle in high temperatures because as the metal expands axially, the tracks are constrained, which applies a compressive reaction force axially. The train tracks may buckle under this compressive force. Diamond cut cans are manufactured thanks to buckling. Fun fact, due to the equalization of pressure, the pattern becomes more distinct when the can is opened. The primary cause of buckling is axial compression, where a component experiences compressive forces along its axis. The critical load at which buckling occurs is influenced by both the geometry of the component and its material properties. Additionally, imperfections such as geometric irregularities or manufacturing defects can accelerate the onset of buckling in mechanical systems. Euler's buckling. Euler's buckling, named after the Swiss mathematician Leonhard Euler, is a fundamental theory in mechanical engineering that addresses the stability of slender columns or structures subjected to axial compression. This theory assumes an idealized scenario where the material is homogeneous, isotropic, and the column is perfectly straight without any initial imperfections. Euler buckling critical load formula. The critical load, P critical, in Euler buckling theory, is determined by the formula PCR, P critical, equals pi squared times E times I over K times L squared, where E is the modulus of elasticity, I is the moment of inertia, K is the column effective length factor, and L is the length of the column. This formula is pivotal in Euler buckling theory as it defines the point at which a slender column transitions from stable to unstable equilibrium. We use this to ensure mechanical components are designed with sufficient stiffness and material strength to prevent buckling under expected loads. But what's the effective length? The effective length, LE, is the distance between inflection points on the deflected shape. For the column with fixed and free ends, the distance between inflection points is twice the length of the column, so the column effective length factor, K, is 2. End connections make a huge impact on the critical buckling load and must be considered thoroughly. FEA application in buckling. As mechanical engineers, the role of finite element analysis, FEA, becomes paramount in understanding and mitigating buckling. FEA allows us to simulate and analyze the behavior of mechanical components under varying loads, helping us predict the critical loads at which buckling may occur. Moreover, it provides a powerful tool for design optimization, allowing us to create structures that are not just mechanically sound, but also optimized for stability and performance. So let's see an example in SolidWorks. We will be evaluating the fixed free column in FEA, as seen here, with one fixed end and one free end where the load is applied. First, you'll make your part. This column is 0.3 meters in diameter and 2.55 meters long. It's a pretty thin column, but it's the one we'll be evaluating today. You'll then want to create a new buckling study. You'll go to the Simulation tab, click New Study, and then do a buckling study. Click that green check mark. Similar to a frequency study, we may want to analyze more than one buckling mode because there will be multiple modes that buckling produces. Right-click the study and select Properties. Under Options, you can change the number of buckling modes. In this example, I picked 5. In most practical cases, the first positive buckling mode determines the safety of the analyzed part, which is usually going to be the first mode that you see, but it's nice to see more modes. Right-click on your part to assign a material. You can find more materials in the Apply/Edit Material menu. Today I'll be using plain carbon steel. Next, fix the base of the column. Just the fixed geometry on the end of the column will do. Then apply the force to the top of the column. I applied about 10 newtons, which is a pretty small force. We'll then mesh and run, and you should get the results. If you want to change the deformation to true scale, right-click Results and then go to Edit Definition, and you'll open this window and you'll be able to click True Scale. You can click through the mode shapes by using the right or left arrow at the bottom of the legend. You should have 5 mode shapes since that's what we selected earlier. Once you have your different results, it may be helpful to right-click the results and go to the List Buckling Factor of Safety. These buckling factor of safety values are how much the applied load must be multiplied by in order for buckling to occur for each mode. So for mode number 1, to find out our buckling load, we'll take that 10 newtons that we applied, multiply that by the 156.3 buckling factor of safety, which is going to be 1,563 newtons, would be the buckling load for mode 1, which is the first positive mode. If the buckling factor of safety is less than 1, then the column will buckle. Hi! So now we'll be doing torsional buckling in SolidWorks, which is slightly more advanced than before, so I'll be videoing it, so follow along with the video. This is a surface extrude circle that we're going to do a new study. Buckling, check. So we're going to make sure that this is treated like a shell. Then select thickness, 1 millimeter material, alloy steel, check. There we go. So we're going to fix this at the edge, and then we will load it with external loads torque. We'll apply this to the face, about this. That looks pretty good. So now you have torque going around the face and it is fixed on the bottom. We are ready to create the mesh. This looks about right. I feel good with this. Very nice. And now we can run the study, which should only take a short moment. Here we can see some pretty cool deformation from bending, and if we want to see even more modes, we'll go to Properties, 1, 2, 3, 4, 5, click OK, and run it again. It should still be pretty quick, so you'll get multiple different mode shapes now. Very, very cool. Then you can check the results, list buckling factor of safety. So our first positive result is mode 4, which is at 909. So this shell loaded with 10 newtons is going to be okay. We'd need about 9,000 newtons of force to see buckling with this piece. So that's great news for us and our 10 newton loaded topless soda can. Thank you so much and have fun doing buckling FEA. Bye. You're going to open your model and you're going to go straight to simulation, new study, buckling. You're going to make sure that you apply your materials. Let's just say plain carbon steel. Go to Properties, and I want to see like 5 buckling modes. As we covered earlier, it's the first positive mode that we want to focus on. We also want to make sure that this is a solid body, which it is. We will then fix one side of this beam. I'm going to just fix this face. Very nice. Fixed. Then for the other side, do external loads, force, and a pretty hefty beam, as we'll say 30,000 newtons. Mesh and run. Beautiful. See the notes. Alright. 1, 2, node shape 3, 4, 5. So we can look at these results, right click on the results, and then list buckling factor of safety. So we can see there's a pretty small factor of safety. So in all of these modes, there is buckling occurring. So we would want to apply less than 30,000 newtons to this part in reality.